We are telling this about variations from software.
Okay, thank you. So today's talk is going to be on classical gravity, right? Even though there will be some quantum gravity in it. We will see how. So let me begin by introducing the problem that we will be discussing. So let's suppose that there is some kind of explosion in space where some stationary system breaks apart into many fragments. So during this process, there will be gravitational waves that is emitted from this, and if you have a detector D that is placed far away from the source, it will eventually detect these gravitational waves. And one such example that we will keep in mind is the explosion of a supernova, right, which will throw out fragments into the space. We can also consider a more general situation, okay, where you have a collision, where a set of objects come together, interact, and then fly apart. And during this process, we will not make any assumption about what happens during this process. They can exchange mass, other quantum numbers, fragment, qualis, etc. And this will also produce gravitational waves. And a somewhat simpler example of this collision is the bullet cluster, which represents a supercluster of galaxies that pass through another supercluster of galaxies, each of these weighing about 10 to the 14 times the mass of the sun, and the relative speed is about 1% of the speed of light. Okay, so I'm giving these examples because later on I'll just mention some of the numbers that one gets from these examples.
And in this case, mostly dark matter.
Yeah, dark matter, exactly. In our case, it will not matter what actually is passing through quantum.
Merger is also covered in this.
Merger is also covered in this. Okay, what we will see, merger is somewhat of a boring example of this, but it is certainly covered in this. Because merger, you will think of this as one object going into multiple objects, because initially you have a bound system, right? So that breaks up into a black hole and many gravitational waves. That's how we'll build the model. So in general, if you want to compute gravitational waves that is produced during such processes, that's a complicated process. And it's complicated because of two reasons. One is that when the objects are close, then those may undergo complicated non-gravitational interactions. And this is what happens, for example, in the case of the explosion of a supernova. The second reason it's complicated is because gravity is non-linear. Okay, it's described by a non-linear partial differential equation. So even if interactions are purely gravitational, and this is what happens, for example, when two black holes merge, even their analysis is complicated, and often one requires numerical techniques to study this process.
Sorry, I have to ask complete aside, but to the extent situations are dominated by dark matter and they're weakly interacting, suppose, is there another situation besides black hole merger where the dominant effects could be purely?
Yeah, that is so. Whenever the other interactions are small, yeah, right, then the dominant effect is pure. Okay. So despite this complication, it turns out that some results in quantum theory of gravity, which are known as soft graviton theorems, those can be used to get analytical results on some aspects of classical gravity. Yeah, this is what we are going to discuss in this talk. Okay, so here are the various collaborators that I have. And I could say that the main person behind much of this is Vishwajit, right? I think he derived most of the results that I'll be describing today. And here there is a short review where you can find these results. Okay. So let me describe the conventions first. So I'll not set any constant to equal to 1. Okay, at least in the initial stage. Later on, I may set some of these things to 1. So we'll denote by c the speed of light, by g the gravitational constant. So space-time coordinates, because I am not setting c equal to 1. Okay, it's not only c times t, and then this is the usual space coordinate. Similarly, momentum, the first component, the 0th component will be energy divided by c, and then the usual momentum components. So I'll be using mostly plus signature metric, which is here with this signature, e square is just minus m square c square. And throughout this talk, all the indices will be lowered by this flat metric. Okay, so we'll never use the full metric to raise or lower it.
You have in mind weak gravitational fields?
No,
But still you.
yeah, still I'll be using this. But I can always define or raising and lowering, right? Okay. So H mu nu we define as the difference between G mu nu and eta mu nu, which is a factor of 2. And so our goal will be to compute contribution to H mu nu, which is of order 1 over r at a distance r from the source of gravitational radiation. Okay, because this is what characterizes radiation from other fields, for example, right? Multiple fields or Coulomb fields, etc. So we'll look at terms of order 1 over r, ignoring all terms of order 1 over r square has. And this is a technical point. It turns out that instead of working with H mu nu, it's slightly easier to work with this combination E mu nu, which is sometimes referred to as a trace reverse metric. Okay, you just subtract the trace part from here. But we don't lose any information because you can also reverse this and you can write H mu nu in terms of E mu nu. Okay, so if we know E mu nu, we can reconstruct H mu nu and vice versa. So I'm introducing this quantity E mu nu because most of the results that I'll be describing will be for E mu nu rather than for H mu nu. But you can easily reconstruct H mu nu from.
But E is not traceless, right?
No, neither are traceless.
Neither.
E nor H are traceless, exactly. Okay, otherwise, if it has traceless, you couldn't have reversed this. Right? So it's important that it's not traceless. So the trace information is also contained in it.
So this inherent of dimensions will be 4.
Dimensions will be 4, yeah. I mean, one can do this for higher dimensions. Their things are simpler. In fact, I mean, the infrared divergence, etc., less severe. That we will be focusing on 4 dimensions.
So with this definition, the traces of E and H are just equal and opposite. Right?
Yeah, that is equal and opposite. Yeah.
E satisfies a simpler linearized equation.
E
Satisfies a simpler linearized equation.
simpler, yeah. Linearized equation, it will satisfy simpler linearized equation. It will be just basically a box E mu nu equal to 0 rather than all these other operators that we have in the linearized operator.
Although you're not working the linearized approximation, the idea that you'd like to compute the gravitational field far away from the object, so
Yes,
that in
certainly.
effect it becomes weak. I mean, is that?
Far away it becomes weak, of course, right? But the production happens at the source.
So it's not so strict.
But we'll see. I mean, that the kind of things that we'll be looking at, right? Things will simplify. Okay, so let me summarize the results and then I'll try to briefly discuss how we arrive at the results. Okay, but I'll try to focus much of my time just explaining what the result. Okay, so here is a more concrete setup. So you'll consider scattering in space because the explosion is just a spatial case of scattering. So you can also consider scattering in space, where we take a set of objects which have 4 momentum P1 prime to Pm prime, which come together, interact, and then disperse as a set of objects with 4 momentum P1 to Pm. Right, and we assume no relation between the prime momenta and the unprime momenta, except that the total momentum, of course, is constant. Okay, so the sum of these will be equal to the sum of these. And in doing this, so the scattering takes place in some point around some region in space and time, and we will be choosing the origin of space time to be inside this region. Okay, it doesn't matter precisely where you take the origin of space time, but we'll assume that the origin of space, that's actual scattering, takes place within a distance of order 1 away from the point y equal to 0. Right? If y is the space time coordinate, we'll assume that y equal to 0 is somewhere in the interior, and the scattering is taking place within some distance of order 1.
When you say objects, they also include gravitational fields.
They also include gravitational fields. Yes. So objects means everything. Right? So in the final stage, we'll have to count also the gravitational waves that come out.
But you have in mind a collision where the ingoing stuff sort of roughly hits at a well-defined time, is it? And then you measure T naught
Yeah,
from.
well-defined time, but it doesn't have to be sharply defined, right? Because finite times, within some finite time they hit that and then they disperse.
Okay, and then T naught is the height of the signal, but measured roughly from the origin of time.
From the detector. So you place a detector far away,
Yeah.
right? And T naught is the time at which the peak of the signal reaches the detector, right? So it will require some time for the thing to reach the detector, right? If the collision happens at say y equal to 0, right, which means around t equal to 0, it will take some time. Right? There's R over C and then there's logarithmic correction because of the gravitational pull on the gravitational wave. So that's what we are calling T naught.
I was just asking that, I mean, the correction you say is due to gravitational drag, but if there's some fuzz and when the collision happens, that will also contribute, right?
Yeah, but that fuzz we are thinking it's a fixed number, right? Maybe 1 light year, right? But some fixed number, right? And we'll look at time scales larger than that, right? So that's the idea, right? So that's why the fuzz will not have affect the final result.
So the process is classical, it's classical in gravity, but other processes involved could just be non-gravitational.
Yeah. Nuclear interactions, there are nuclear forces and so on.
But in gravity, it's classical.
Yeah.
Leading order Newton constant.
Leading order in Newton. Well, no, not leading order in Newton's constant. Because we'll be iterating, not necessarily leading order in Newton's constant. Right? It's just there's no H bar. That's all.
Right, okay.
Right?
No, but H bar could come from other phenomena.
Yeah, if they're hitting the H bar, right? That is in the nuclear force, for example, that we don't care. Right? As long as you can describe it in terms of some classical force law.
Yeah.
Right? The origin of the force may be quantum mechanical.
So how does one see this precisely? So this, what is the limit in which we are describing this?
The limit is just considered classical. The final state is classical, right? Even here, if the quantum gravity effect doesn't really matter.
Oh, I see.
Right? Yeah. If you think of there is quantum gravity effects going on here, that's okay.
That's what I see.
I thought you were just going to solve the classical GR equations.
Effectively, we will do classical GR equation, but what we'll see is that what happens here doesn't really matter.
That's even more powerful.
Yeah.
Is there a precise definition of gravitational drag?
Yeah, one can calculate the trajectory, right? If you think of this as Schwarzschild metric, for example, right, and see how much time it will take to climb up
Oh,
the potential. So that's
what you meant.
That is what this R star, right? That's a T equal to R star. That's a null.
Yeah, but I'm sorry, you didn't say that this is a black hole or you're saying
Well,
it could be or it could be.
Yeah, it could be some.
It could be anything.
It could be anything,
a star,
right?
just a
Yeah, far away it's that.
far away it's Schwarzschild.
Yeah, it's Schwarzschild.
And just that. Okay.
That drags, right?
Okay.
So log R. That is.
The correction is because you are considering like a correction with respect to flat.
That's it. Yeah. But ultimately, it will not really matter because as long as there is T naught, is roughly the time when the signal reaches the detector. Right? That time scale again can be defined over a year or a billion years, right? It can, but ultimately, we'll have to look at time scales beyond that. Okay, we'll see. The uncertainty in T naught will not matter, right? Then the reason we'll see when I write the formula, right? Why the uncertainty in T naught doesn't matter.
For you to treat this as a classical problem, would you also need some kind of unitarity, restricted unitarity, which makes sure that semi-classical states capture the semi-classical states?
Yeah, I'm just thinking of this as a classical process that happens in astrophysics, for example, right?
Okay.
Where the incoming and outgoing states are semi-classical.
But if there's a quantum process which states like semi-classical states to some weird quantum states, then we can't do it.
See, I'm thinking of the final state being described by states carrying certain momentum, right? That will be good enough. The objects carrying certain momentum. Yeah.
Sorry, but what exactly is classical in this?
Well, you think of it as classical scattering, right? I mean, the astrophysics is, I think of astrophysics as classical.
No, but you said formalism allows for even quantum effects.
In the interior, what happens, we'll see, it doesn't really matter.
But that's the scattering, right? That's the
That's the scattering, yeah.
Yeah, so
Yeah.
what is classical?
Well, the final states are classical,
But final, what does this mean? Final states are classical.
very heavy, right? They don't have quantum fluctuations. They're much heavier than the Planck scale, for example. That's the classical limit. I mean, think of the classical limit as the limit when the final states are much heavier than the Planck scale.
It's waves, gravitational waves, they are coherent states, which are just
Yeah.
well described in the class.
That is true, yeah. But they are also carrying energy, which
Yeah.
is large, right?
Just-
Okay. So we define retarded time.
So this is in contrast with the usual asymptotic states that we have in collider experiments. Because there also, I mean, if the electrons are coming scattering away,
Yeah,
that's also you would call it classical final states.
that is true, but they are the way will detect, I mean, if it is doing quantum gravity, we'll detect individual gravitons, right? We'll not think in terms of the flux or the waveform,
Okay.
right? Because you'll be describing gravitational field using this waveform,
I see.
right? Whereas if you are doing the collider experiment, we think of photons being collected, right? Not
I
some
see.
classical electromagnetic
Thank
field.
you.
But it's in that sense that gravity will be treated classically, right? As a waveform. Okay, so we define a retarded time, okay, which is here. And what we are going to focus on will be the late and early time tail of the wave, which will be the value of h mu nu at the detector at large positive u and large negative. And the idea is that here u is defined only up to shifts of order 1, because T naught, order 1 can be right here, right? But some fixed number, because T naught is only defined up to shifts of that order. Not affected by that shift. Okay, so let's see what are the terms. So the statement is the following: that we'll be looking at terms proportional to R inverse, okay, because we are looking at radiation, and we'll be looking at large negative u, that means on the early time, we'll look at tails of the form 1 over u times the coefficient, then 1 over u square log u times another coefficient, and then order u to the minus 2. So you see that here, for example, if you shift u by order 1, then for large u, it's going to affect the coefficient of the u to the minus 2 term, but not the coefficient of the u to the minus 2 log u term. Okay, so these coefficients are not affected by shifts of u of order 1. Similarly, at late time, we look at coefficients of this kind, coefficients of terms like this, of this kind. And again, we see that if you shift u by order 1, right, none of the coefficients a, b, and f are affected, but this can be affected.
T0 was the time of the
T0 is the time, T0 is the time at which the peak reaches the detector, right? So you say the detector, you have a detector, right? The bulk of the signal reaches you at some point, right? And you're looking at the time which is way past the peak or way before the peak, when the peak has reached you. Right? Those are the times at which you'll be looking at the signal. Okay? The reason being that those are the times for which you can say something, right? Without going through the details of the scattering process.
But U is much larger than T. It's
U need not be much larger than T naught. T naught is actually not relevant, because T naught is dictated by how far the source is from the detector, right?
Yeah, but
So that can be very large. U doesn't have to be larger than T naught.
I think you're not giving the times at which the collision is happening.
Okay, suppose we have LIGO, right? It detects signal from black hole merge at billions of light years, right? It takes billions of years for it to reach the detector, right? We don't have to wait for billions of years, right? We wait for the signal. In the LIGO detector, we wait till the signal has some strength, right? The bulk of the signal, right? We cannot say about very much, but the tails, right? Way after the bulk has passed, or way before the bulk has started growing, those are the time scales at which you can say something, right? So U doesn't have to be larger than T naught, right? U just has to be larger than the time that it took for the process to happen, right? The division and scattering took place during some time, right? U has to be just larger than that.
T0 is just a shift to the Earth's frame in what you.
Yeah, exactly. T0 is just a shift to the Earth's frame, that's all.
And the very early time, is it some classical analog of initial state radiation or something?
It will be like that, yeah. It's a final time which is more complicated.
And how do you know that terms are like u to the minus 2 log u, not for example u
No.
to the minus 1 log u
Yeah.
or
So that's also part of the result. Right?
part of the,
Our result. That the result is that it has an expansion of this kind.
oh, that's the result, I see.
Yeah.
Okay. I thought you assume this and then find something about ABC.
No, we prove this and also at the same time find something about ABC. So what we find about ABC is that these coefficients are given solely in terms of the four momenta of the ingoing and outgoing objects. And it doesn't require any knowledge of the details of the scattering process.
So that's the second statement. The
That
first
is
is
second
that this is the form,
Yeah,
and then second statement is that these are.
that these are given completely by the four momenta of the incoming and
That's
outgoing.
not guaranteed by the fact that you.
No, that's not guaranteed. So these are independent facts. Right? The first is that it has this expansion of this kind, and that is given by the four momenta.
And the alien can be large in the sense that it need not be order G Newton.
It need not be already.
Order G Newton. As in this A mu is that a constant matrix?
Yeah, these are all constants. That's how they don't depend on you.
It will not depend on
U dependence is here. So we are looking at we have placed a detector, right? The detector time is U, right? As U becomes large, right? You get the final E mu goes to a constant A mu, and then there are tails, which are these.
So this is like the memory,
Yeah, this is like the memory,
and then there is the tails of memory.
and then there are tails. Right? These, the fact that at a large negative you have set E mu equal to 0, that's a choice of convention, right? Because that basically says that initially you start with eta as the metric, right? Because you could have changed that to some any other constant, right? By changing coordinates. So that we have not done, right? We keep eta mu as the initial metric. So that's why this is 0, right? But then on top of that we have these features.
So this, so the time that is relevant for this result is that you have this process, and then this process, let's say, is it's a lot of radiation from this process at particular time, but you are interested in time much after that.
Exactly.
And also from this side, before the light ray would reach there.
Exactly. Yeah. Like this bullet cluster, for example, right? The time scale will be larger than the time scale that it took for the clusters to pass through inside. Right? That's the kind of time scale, right?
Right.
For black hole merger, right? It will be like initial state, of course, there is inspiral, that doesn't really matter. The final state is important. There will be roughly the light crossing time of the horizon, right? Because that's the kind of time it takes for the merger process to take place, right? The quasi-normal modes, etc., die off within that time, right? The light cross horizon, the light crossing time, so it will be larger than that time scale.
Also, I mean, there is this intermediate time scale, which is also large, where so let's say the process is happening at a particular point in space time.
Yeah.
And detector is, let's say, one line. Then from here you can shoot
Yeah.
up this
So
past rays and the future rays. There is this light.
But that has no relevance.
That is no.
So
So you.
that is T0. See, that is T0, right? But that we basically subtract, right?
Yeah.
Because T minus T0 is the detector's time. The time that it takes for the signal to reach the detector, right? That doesn't really enter anywhere.
That doesn't really.
Right? Except R. R, of course, that's controlled by R.
Yeah.
Right.
And Ashok, although the 1 over u tail, the terms are small, the ones going like 1 over u, A mu is of course not suppressed like this, but even if you look at the 1 over u terms, they are small, but they give you direct information in a sense about the ingoing and outgoing
Exactly.
momenta. Right?
Yeah.
So to that extent, if for example you were interested in something like how much of the mass of the bullet cluster is accounted for by visible matter,
Yeah.
to make a case for that,
Yeah.
then this is a good way to try and do it
That
because
is
it's
true. Yeah,
independent of the details.
Exactly. Yeah, it's independent of the details, right? But it only depends on the incoming and outgoing.
And the memory is not even suppressed in a sense.
See, this is also not suppressed. I mean, what this 1 over u times v mu nu will be roughly of the same order as mu nu. for a generic scattering process, when U is of the order of the scattering time. Right?
I see. But I thought you had to be much bigger, you know?
But much bigger than of the order of the scattering time, right? Suppose the scattering time is unit 1,
I
right?
see.
So the memory sets in after the scattering time, right? At the same order of time, right? Maybe it will take 5 times that time, then there will be 1/5,
1/5,
Right.
okay.
and that will multiply the period.
I see, you're saying it's not like a parametric sum. In essence.
Exactly, yeah. Because I mean, you don't have to take infinitely large, right?
Yeah.
If you want infinite accuracy, then of course you have to take U to be
Yeah,
infinitely
yeah.
large. But as I said, for the black hole merger, right, it's enough that U is larger than the quasi-normal, the inverse of the quasi-normal frequencies.
I see.
Okay, so now I'm going to show you the formula for this, right? The actual formula are very complicated, but that's not really important. Right? So there are some features of that formula that I'll explain. Okay, but this is just to convince you that the formula exists.
Sorry, can you go back? So this was this is describing the gravitational field.
Yes.
And the assumption is that you know the ingoing and outgoing.
Yeah. If you know the ingoing and outgoing momenta,
momentum, then you
Right.
know
then you know these constants.
so in these fields, I mean, in these objects whose whole momenta you know, this gravitational waves are not thought of as part of that.
No, they are part of that. At this stage, they are part of that. Yeah. Later on, we'll try to see how to get rid of them.
Okay.
In this formula, they are all part of that. Right? Those will enter the formula. So I'll just show the formula.
Okay.
Right? In which case, you have to include also the gravitational waves. So here, you can see that. So let me define this various things. So R is mod x, that's the distance to detection. Right? N is essentially the direction of the detection, where you place, which direction you place it. Right? So it's first component, 0th component by design is 1, and then this is the direction cosine. So it's an null vector. And you can see that everything else is determined purely in terms of the momentum, right? This is the outgoing momentum, this is the incoming momentum, right? All of these involve only the outgoing and ingoing momentum. And as Abhijit just raised this point, that this includes, for example, this is the final state momentum, this will have to include the sum over the final state gravitational waves, right? Whatever energy they are carrying away, right? That's also included in this.
You'll define, as you were saying, some way to associate a momentum, maybe with a wave packet or something.
Yeah, our classical gravitational wave carry momentum, right?
Okay.
You can define by Fan-Noether procedure.
The total.
Yeah, the momentum at each angle, right? You know what momentum flux is going on,
I see,
right? That's from the gravitational wave formula,
I
P
see,
mu nu,
I see,
right? That's what we can use.
I see. So this sum will
Would include that
have
also.
some kind of an angle.
Exactly.
integral.
Yeah, angular integral, exactly. So the sum will involve an angular integral over that gravitational waves, which are limited.
Those MA should be zeros. The gravitational wave.
Yeah, for those are images should be 0. Right? But it doesn't completely vanish because you can see these things are still there.
Sorry, what were the emits?
The masses. M's are the mass. So P square is M square. M square is minus M square C square. So here I'm thinking of these as some particles going to particles, right? But you can easily replace it by waves by thinking of the gravitational wave as a flux of particles.
So here gravitational waves are assumed to be, the background is assumed to be flat or the swart.
Flat, because you are looking at far away, right? As a director. So if the background is flat. Because background is flat up to 1 over r collections, right? And because we are keeping only 1 over order 1 over r terms, we can just ignore the effect of the background.
So the immediate next order will be affected by.
Yeah, immediate next order will be affected. At 1 over r square, but at 1 over r order, there is no. The background you can think of as flat. So here is more complicated formula for the next 1 over u square log u terms, right? But the important point is that these again only depend on the incoming and outgoing momenta. So now let me describe some features of this formula. So here, as we already heard, that this term, right, basically tells us that even after the gravitational wave passes through, the metric doesn't come back to eta mu nu. You start with eta mu nu, the gravitational wave passes through, the metric doesn't return to eta mu nu. Instead, it returns to eta mu nu plus a mu. This is what is called a memory. Okay, that the gravitational wave passes through and then the actual metric changes, right? So if you start with a interferometer which is in the destructive configuration, by the time the gravitational wave has passed through, you are not back to the destructive configuration, right? Unless you actually restore them to the original configuration.
This is not pure gauge, like this is mechanical.
This is pure gauge, but it's not pure. The change is not pure gauge. In the final
The capital A. The capital A.
capital A, yeah. So in the final state, you can make a change of coordinates to make it eta mu nu, right? But the fact that it has changed from
Oh, I see.
0 to a mu nu, right? That is not pure gauge.
In same coordinates, it's different.
Exactly. In the same coordinates,
Coordinates shift around.
exactly. Right? You have to then rescale the coordinates from what you started with.
Yeah.
One might imagine, sorry, changing the coordinates after a certain, I mean, slowly, diabetically through some time, right? So that later, after
Yeah.
some time, the coordinates are the ones which take away this a mu nu, and before they are the old coordinates where a mu nu was 0.
That is true. Yeah. Yeah. But
Then
during that
something will
change,
happen during that change.
yeah. So
obviously.
during that change, the metric will change, right? There will be
That's,
because
yeah.
coordinate
In a way,
change
that's
induced.
the invariant thing that you are
Yeah,
measuring.
exactly. It's
That
like
you measure.
the change of, I mean, there's an analog of electromagnetic memory, right? The A0, for example, changes,
Hmm.
right? Now A0, of course, you can say
It
A0
always cannot be taken
yeah,
zero.
can be taken to be 0. Not A0. I think it's something else, some transverse component of A changes.
Hmm.
But the time derivative of that, of course, is the field strength, right? So it basically says that there's an integrated field strength, which is
Right.
which is the gauge invariant object, right? That cannot change.
Is there a similar description here, like in one writer, if you model invariant quantity that shifts?
With curvature.
Probably, yeah, you can probably rewrite this as an integral curvature or something, right? I've not seen it done, but it can probably be done.
Maybe a Wilson, a gravitational Wilson line.
Yeah, exactly, something like that.
Anyway, the way you describe it is, of course, very physical at LIGO. Can they actually see this? I'm just curious.
No, they cannot see this because the way the LIGO is built, there's a restoring force, right? So before the memory turns in,
You see, the mirrors adjust.
yeah, mirrors adjust themselves because of the restoring force, but Lisa is supposed to see it, right? Because that's in space, right? In space, there's nobody is going to come and push it back to the original configuration, right? So there you will see, one should be able to
Right,
see.
even on the ground, nobody comes and pushes it back. Like,
But on the ground, something is hanging, I mean, it's hanging on some torsion balance, right? I mean, there's some spring which actually turns it and,
you could have a spring in, but I don't know what that would do here.
yeah, I mean, there is some mechanism which turns it back to the original configuration.
So it's constantly monitoring for constructive interference in a sense.
I think, so yeah, I think after every passage of the gravitational wave, it brings it back to the destructive.
Destructive,
Do you know what is the order of magnitude
Of this
memory term?
memory term, yeah, so it's just about LIGO sensitivity, I think, right? That for this binary black hole merger, I mean, what I've heard is that if LIGO didn't have the restoring force, it might even have seen it.
They can't switch it off for some days.
No, I don't think that it's a hardware thing, so I don't think they can switch it off very easily.
And it would just accumulate, right? So it would be easy
Yeah.
to take. It's not a matter of even this resolution, right? Because
Yeah.
keep on accumulating.
Exactly,
That's-
but the accumulation may happen always, it's like random walk, right? Because a mu can be negative also, right?
Yeah.
So it's like a random walk, but yeah, it will accumulate the square root of t, right? If you-
It's again.
you keep it like that.
At least.
For subsequent events.
Yeah, exactly, for subsequent events, it will keep accumulating, right?
But since it's a tensor, it might not just follow that. Might be something.
Okay, maybe something else, but that is, I have a feeling the square root of t probably will still remain, but.
Could be, yeah.
Yeah,
Right.
okay, so these memory terms were of course known earlier, right, in fact from the 70s. Okay. But it was given a new push after the observation that this follows from software. And that will, because this mu actually, this whole formula came in a sense from software. these terms, okay, people have seen some tails, but there is no universal formula for such tail terms. Yeah, these you actually get from soft theorem. The first it was derived from soft theorem, but I'll also describe a classical derivation. Right? Because it's a classical gravity process, so there better be a classical derivation. Right? But it's easier to understand from soft theorem perspective. Okay, so this is something that I've already said. So here are some features of this formula, that these can be expressed in terms of the momentum of the incoming and outgoing objects, and you don't need to know anything about what forces operated and how the objects move during the scattering. It just is fixed by the initial and final configuration. So this is a consequence of the soft graviton theorem. And in contrast, if we have to compute this waveform at finite time, that will depend on everything. That will depend on everything, right? It will depend on details of the scattering process, what kind of forces acted on them, on the objects, and so on. So that's a much more complicated calculation.
So Ashok, these quantities A, B, C, F, G, are they expected to obey any sort of relation?
Not okay. There are some gauge invariant conditions, right? That if you replace, if you contract K mu with H mu, or N mu with H mu, that N is the direction of the momentum, right? Then it should give you 0.
So that's already built in.
That's already built in, yeah. Meaning it's built in the sense that you derive this formula in general and then you check that it actually satisfies that formula.
I was wondering if there's some positivity or something which may end up constraining
Some positivity,
the
I see.
initial final momentum coming from unitary. I mean, this was just a way.
Okay, yeah, it could be. Yeah. In fact, we will discuss at the end that there is a hope that there are infinite number of formulae like this, that universal terms like this. So in principle, you have infinite amount of data for initial and final momentum, right? And the question would be whether you can actually reconstruct, whether that data is sufficient to reconstruct the full scattering.
Infinite amount of data because we can have any number of momenta or what?
No, okay, the scattering has a lot of data, right? Incoming and outgoing. We don't know how many particles went in, how many particles went out. But the data is in the sense that how many of these coefficients we have. But this is what we measure, right? In the detector, we can intensively measure these coefficients, right? And the idea is that the higher order terms here, right? Like u to the minus 3 log u square, right? Or u to the minus 4 log u to the log u cube. Those also you expect are inverse, right? That they are given purely in terms of the incoming and outgoing. We don't have a formula. I mean, that's it. But the expectation is that those will also be universal.
So it's just to understand, at 1 over u cube, you have a term going like log u square. Is that right?
1 over u cube log u square, yes.
And so it's always the leading logs at whatever
Exactly.
that you think is.
That's right. Yeah. I mean, we certainly know that for electromagnetism, this is true, right? There you have the formula, right? And typically anything that is true in electromagnetism is also true in gravity, except that the formula is more complicated.
So in electromagnetism, we have the formula for all such terms.
All such terms which are of this kind, u to the minus n,
Yeah.
log u to the n plus 1, yeah.
For all of them.
Yeah, for all n.
So there you can reconstruct all the charges.
Well,
Is
I
that-
think
is that the idea?
for 2 to 2, right, we cannot reconstruct all the charges. The higher orders, we are still trying to see if the data is enough to reconstruct all the charges and momentum, right? We don't know yet, right? It may be that there is some internal relation between these coefficients, right? So that it leaves some combination of the charges and momentum undetermined.
I see. But 2 to 2, if you went to all orders in electromagnetic.
Even then, you cannot do it, yeah, that we have checked.
Because of basically relations. I mean,
Yeah, because 2 to 2, what happens is it's simple process, so that the scattering depends only on some very particular combinations. Right? But that is not the case for higher order. Right? For higher order, at least it looks like there is a non-trivial dependence on very different combinations. But for there's a hidden relation that prevents us from reconstructing the whole thing, we don't know. Okay. So this is again something that we discussed. The expression for A, B, and F, which are the final state results, right? Let's go back here. If you look at this, you see that C is the initial state. What happened at past, right? This depends on the incoming moment. A and B depend both on the incoming momentum and outgoing momentum.
The outgoing is P
P
and the ins are prime.
Ins are prime. Okay, so A and B depends both on the incoming and outgoing, and the same is true for F. It depends both on incoming and outgoing momentum. G again depends only on the incoming.
Sorry, Ashok. You said that the initial state and final states are classical, but if one were to consider this process where you have some amplitude of scattering into various things, so just a scattering amplitude as a quantum object, then what can be said about the field?
I think if you can describe the gravitons, the gravitational wave part as a waveform, right? These formulas will still be valid. Right? It's important that the question is whether you can think of the gravitational wave as a waveform.
Okay.
Right? That's the important point. I think when we discuss the derivation from soft theorem, I think it may make it clear where exactly the classicality is playing a role.
No, but for example, in the supernova, etc., quantum processes might be going on even.
Then it doesn't matter. That doesn't matter because the gravitational wave is classical.
No, but initial final guys also could be quantum, right? It would be very fine particles. I mean,
That is actually okay. If it's many neutrinos and other things are going apart, that's not a problem.
but then there would be quantum states, right? So there will be this process which would be described in terms of an.
But the final flux of neutrinos and various charged particles, right, can be described by classical average flux.
Okay.
I mean, the back reaction on the metric would lead to a classical.
Exactly. Yeah. The back reaction on the metric will lead to a classical gravity, right? I mean, individual particles may be quantum, but collectively, you can talk about how much is the flux of energy in a given cone, right? And that's a classical quantity, even in supernova.
So one is kind of taking that is some expectation value of this cluster cell.
Yeah, that's right. Yeah, exactly.
Source.
As far as the gravity is concerned, I think it is good enough to think of this as an expression.
Ashok, this F and G which were up there, these are for future and past coefficients.
Yeah,
Some
G, yeah,
same
A is
kind of
future,
thing,
G is
right?
past.
So there are some terms which are identical, like looks like the last term is the same upward sign, but some
Yeah.
terms are not at all similar.
Yeah, it's same meaning, it's replaced prime by.
Exactly.
Yeah, exactly.
But that's only the last two lines.
Yeah.
Then there are some middle terms on the top which are not there.
Yeah. So these are, I mean, somehow related to backscattering effect,
Okay.
right? Which is the fact that we use retarded Green's function, so there is a asymmetry between the past and the future.
Thanks.
Yeah. So here is the confusion, right? That because this A mu, B mu, and F mu involves a final state momentum, right? These also include contribution from gravitational radiation, right? Because the outgoing flux of gravitational radiation, we have to also think of as momentum carrying object. And we can either think of a flux of massless particles or just some classical flux carried by the gravitational wave. Right? It's the same thing, but that has to go into the formula. And this, in fact, again had been known for mu for the memory, and this is what people call non-linear memory. Right? This happens because gravity is non-linear, right? So this scattering produces gravitational wave itself. And for memory, if there's no way to avoid it. Okay, that's for memory. Yeah, if you want to calculate how much memory is there in the binary black hole merger, right? You have to calculate plus what's the gravitational wave flux, calculate the integrated contribution to the memory, and that's how you can calculate it, right? So without finding how much gravitational wave flux was emitted, right? You cannot estimate what the memory is.
But that's true for any process involving gravitation.
In principle, yes. So in principle, that's true also for B and F, right? But we'll see that somehow there's some miraculous property of this formula for B and F, right? That allows us to express the contribution from massless final states in terms of the massive final states. Okay, and I'll tell you what the formula is.
Does that make it independent of gravitational radiation or somehow the effect
No,
of
it's not
gravitational
independent.
Radiation is
Is
incorporated.
Exactly, right? So I'll give you the formula, then it will become clear, right? What one means by you can, replace gravitational waves with something else. Replace the final state massless particles by something else. And this is true not just for gravitational waves. Electromagnetic wave is also the same. You can, remove that contribution. Neutrino flux you can remove, right? If you think of the neutrino massless or almost massless. So here is the observation, right? That in the expression for B mu nu, we just drop the massless particles or radiation contribution from the sum over final states. Okay, only contribute sum over massive final states. And then we compensate for it by adding a contribution like this, where Pi is the total incoming momentum and Pf is the total outgoing momentum that is carried by only the massive particles.
But PI includes incoming by massless or?
Yeah, Pi includes incoming. See, incoming massless, you don't worry too much because, that depends on what initial state you give, right? There's a final massless particles which are the troublesome ones, right? Because they have to actually calculate the total radiation, right? This finite flux we are talking about. We have to do numerical relativity and so on. So this allows us to avoid that problem. That if the final radiation you can omit, right? And in the compensating part involves only the momenta carried by massive particles. So Pi is the total incoming momentum, and Pf is the total outgoing momentum that is carried by massive particles. Right? So the fact that Pf is not equal to Pi is basically encoding the information that some massless particles have gone, and that's the only information in it.
But it could be that the incoming radiation has lots of incoming particles have lots of radiation in them, some of which goes through.
Yeah, so those will be included.
So they'll be included in Pi, but they'll be removed from Pf.
Yes, that's right.
And this miracle, by the way, happens also in QED, I mean, in electromagnetism, where you.
In QED, actually, it's not even necessary because massless particles there travel with the speed of light, yeah, so they don't carry charge. So you can guess this miracle is not needed there. Right? It's only in gravity because massless particles also act as source of gravity.
Then maybe in Yang-Mills somehow.
Yeah, Yang-Mills things are more complicated, so we have not tried Yang-Mills. For this.
Non-confined. N equals 4 Yang.
Yeah. Yeah. Okay, and the similar miracle happens in the AFM, right? We just drop massless particle radiation contribution and then add this term. Now again, this why this happens, you don't really formula and try to see whether the massless particle.
The original formula?
This formula here,
Oh,
right?
achha.
These are both massless and massive everything, right? So the point is just look at the massless particle contribution, right? Some simplification occurs because the m square terms go away. And then you try to manipulate that contribution and you find that the final result can be expressed in terms of this total momentum that the massless particles have.
And which one? F is the late time and
F is the late time, G is the early time. G we don't try to manipulate because G depends only on the incoming.
How did you expect that this might happen? That you can remove the master?
The point is we had seen this happening for B mu by accidentally somehow, right? For
Yes.
B mu it's a little easier, right? And then I said, okay, if it happens for B mu, why not try for F mu, right? To see if something like this happens.
But maybe the same thing happens for the early radiation terms, I mean, the.
It may happen, yeah. We didn't try to look because the point is for
Okay.
early radiation, we don't really care, right? Because if some radiation is going in, okay, we know
You know,
what is going in, right? It's the what is coming out, which is the problematic one, right?
Immune also.
No, immunity it doesn't happen, right? That's why calculating memory is very hard, right? You really need the full numerical relativity. Even in black hole merger, for example, right? You cannot calculate memory unless you have figured out what happens. Okay. Okay. Yeah, so I think this I have already said. So now, if the incoming and outgoing objects carry charge, we have assumed in the formula that they are chargeless. Right? If they do carry charge, then the formula get modified, but it's still, the modifications are known. Right? You have to basically take into account the electromagnetic force between the final state particles and initial state particles. So you can modify the formula appropriately to get the correct formula in that case. Right? Which leads us to emphasize that for charged particles there are additional corrections.
This additional correction is due to the field that they are also, these charged particles are carrying.
Yeah, the fact that the charged particles continue to interact by electromagnetic force, right, that leads to these additional terms. Okay. And then the explosion, right? Clearly, explosion can be regarded as a special case of scattering, okay, where the initial state has just one object and it breaks apart into multiple objects. Okay. In that case, C mu nu and G mu nu vanish, right? You can see from the formula. And G mu,
Assuming no massive particle coming out.
no, initial state, the
Oh,
C mu nu and G mu nu is the
yeah.
initial one, right?
Yeah, right.
Initial ones and don't
Yeah.
care about the final state,
Yeah.
right? So these actually just vanish. Okay. And E mu nu then has this structure that in the final state has this expansion. And now we can focus on the binary black hole merger, right? Which has in the final state one massive object and many massless objects. And for such cases, we can use that simplification, right? We can just remove all the massless particles and then add the compensating term. And then one finds, in fact, that these coefficients of 1 over u and log u over u square vanish. Okay. So for binary black hole merger, there is no 1 over u or log u over u square terms in the expansion.
In the final state.
In the final state.
But just one thing is really unclear is in the merger, do you start with the initial state having two black holes?
No, I would think of this as a one black hole. It's a bound system, right? So you don't try to predict what happens initially, right?
Okay.
I mean, initially will be very far. I mean, then of course the high frequency modes are coming, right? Because of the inspired mode. Right? So there you can really say what happens in the final state.
So you start in a sense after, I mean, just after the, at what stage do you start? So
After the quasi-normal modes are died.
after that time. So you really think of it as a single black hole.
Exactly.
Okay, all right.
But then, what is the difference between the initial mass is different?
Mass is different, yeah. Exactly.
But that change of mass does not give rise to any of these.
Anything because it gets compensated, right? Because the change of mass, there is a contribution from this formula, right? You can say B mu nu, right? The initial and final mass is not the same, but that gets some. Once you remove the massless particle contribution, right? You have to add the compensating term, and that basically cancels. Yes.
Is there a reason we expect it to happen?
Yeah, I mean, I think the various people have various takes on this. Some people say there is something called Price's theorem. Right? The Price's theorem is not really a theorem, right? It's some conjecture which was made at some point. Okay? The conjecture was on not at null infinity, but at a fixed point. I mean, if you take a fixed star and wait for infinite time, right? There is a theorem that it should fall off with time sufficiently fast. Right? So that's again, as I said, a conjecture based on some numerical studies that were made earlier. Okay? I don't think there is complete proof that this should have always happened.
So basically for a black hole merger, B mu nu and F mu nu vanish.
Yes.
And A mu nu is the only effect.
A mu nu is
that
only
comes here.
exactly.
And so what about C and G in that case?
C and G, the point is you don't try to calculate because the initial stage
Is a bound state.
is a bound state where already some radiation is happening, right? It's not a static object.
Yeah.
I mean, the way we had set up the problem, that the initial objects, right, were not radiating by themselves.
C and G are not relevant to this problem.
Exactly. I think C and G are not relevant to this problem for a binary black hole problem.
And can this result be a good check on the numerical relativity simulations?
In principle, yeah. Numerical relativity simulation. The point is, I think they haven't even found the memory in the numerical relativity simulation. But if they find the memory, then certainly it will be a good check on that they shouldn't find any 1 over u or log u over u square terms.
Seems like memory is something you can calculate quite easily, so
Well, so we cannot calculate very easily because we need the information about what radiation took place, right? What gravitational finite energy frequency gravitational radiation took place. Because for A mu nu, you don't have this luxury that we drop the massless final set contribution.
So you need to know the P primes.
Yeah, the P primes are the incoming, you need to know all the P's.
P primes are in, no.
Yeah, P primes are
Oh,
incoming.
incoming, sorry, I got it.
Right. You need to know all the P's,
P's.
right? Including the ones that are carried by the massless particles. Right? That's why memory calculation is harder.
So you need to know what, the details of the process or?
Yeah, I mean, if the numerical relativist tells you how much radiation came out during the binary black hole merger, then you can tell how much memory there will be.
So from the LIGO waveform,
Yeah, from LIGO waveform, I think one can probably work out, right? You will of course need the whole flux everywhere, right? Not just at one angle. But if you reconstruct the event from LIGO, you can actually know what the radiation in different directions are. Right? And from there you can, I think, yeah, because you, identify what kind of black holes merged at what angle, right? I mean, that will do the best fit.
This seems important enough that they should have done it.
The memory.
Numerical people.
Yeah, I think memory, they have not found memory directly in numerical analysis.
But you meant observationally, if you have the LIGO, is that what you meant?
Yeah, clear. No, okay. What I meant is the following, that LIGO observes a waveform, right?
Yes.
From there, they reconstruct the event,
Yes.
right? Once you have the event.
It sees at one direction.
Yeah, it says in one direction.
Reconstruct the whole thing,
Exactly.
but then you get you reconstruct the event, now you know the whole thing.
Exactly. Once you reconstruct the event, right, they have the templates, right? For any given event, they know waveforms in all directions, right? Using that, you can now calculate how much flux went in various directions, and that will tell you how much memory there should be.
Now, then from this, it sounds like it's doable. So you're saying some.
To calculate memory, yeah, but to calculate memory directly, right? So suppose you have a detector, right? You run your program, H mu evolves, and you should see that the H mu evolves but doesn't come back to zero, but to some non-zero constant, right? That I think has not been done in the numerical simulation.
You know, in LIGO, I'm saying only in LIGO it can.
LIGO detector, you're saying.
Yeah.
Yeah, in LIGO detector, because of the restoring force, you cannot see it, right? Because
No, from the detector you can reconstruct the event.
yeah, you can reconstruct the event, and from there you can reconstruct how much memory there should be.
Yeah. So then, which is the situation where you can't?
I'm saying if you just do numerical analysis, right? Or you're constructing a template, for example. You take a pair of black holes which are merging, right? And you construct the waveform from numerical analysis, right?
Without any detection.
Without any detection, yeah, just to construct that in computer, you construct the waveform, right? And that waveform should show that it doesn't come back to zero.
Right.
Right.
Okay.
I think that they have not seen in the numerical analysis.
but can they not see that, but see this the next order numerical analysis state?
Next order,
I mean, because that is that is universal, right? I mean, in this sense.
that is true. Yeah.
So
but
numerical people.
I think it's of the same order. So if they haven't seen that, right, they will not be able to see the 1 over UTL also. But if they manage to see that, then they will be sensitive to the 1 over UTL. I think
But
then,
one of these doesn't have a lowest order term, right? The B.
yeah, so B we are not worried.
Uh,
It's the A, which is the future,
yeah.
right? Because LIGO
Okay.
is
LIGO is
evolving in the future,
evolving.
right? Yeah.
So that's really a bit.
And these, just to understand, the templates are constructed using numerical relativity.
That's it, yeah.
And
Some analytical results in the initial stages, and then you combine with numerical relativity, right? And then you use the quasi-normal modes at the end.
okay, so you sort of match it initial,
Exactly.
final, through some kind of analytics, and then you have the.
Exactly. Yeah.
Thank you.
But these past tails which you're calculating, those are the B and F now, right?
Yeah, past tails are DNF. So those are not there.
These are not measurable things, or what is it?
No, past tails are not DNF, past tails are CNG.
Yeah,
CNG, sorry, I
Yeah.
keep mixing up.
Yeah, CNG, yeah, at least in the black hole merger, they are not measurable because the past in this case is not like a set of objects coming together, right? The past is really an active object, right? You think of this as one system.
It's
which
not
is
experimentally measurable.
no, in the initial, the in spiral phase, right? People do measure, right? But the in spiral phase is a past, right? But that is not covered by this analysis, right? Because here the in spiral phase, right, is an active object, right, which is radiating gravitational wave by itself.
Right.
Right. We are thinking of them as some objects coming together
And that,
and scattering.
but I thought we agreed that even if there's radiation in the initial state, it doesn't matter. Now somehow.
No, that radiation is happening because of the interaction between the initial particles. Because even in the initial state, these things are accelerating, right? That causes some radiation. That is captured by this. But if the initial objects are active, right? Imagine that you are in a spaceship and you are sending out gravitational wave signals, right? That you cannot capture by this universal formula, right? Because that depends on your wish, right?
Okay.
Whether it will send the gravitational wave or not.
But I mean, would it be that the initial states? So I guess the point is that once you understand all the things that are going in,
Yeah.
then you know the initial state is fixed.
Yes.
Right? So I mean, it's not like you could change it, and that change should be seen then in the future. Sorry,
Yeah. So all I'm saying, the initial state, right? The individual incoming objects, right? We are thinking of this as inert objects.
Yeah.
Right? That those themselves are not active, right? That imagine that there's some kind of pulsar, right? Which is sending out electromagnetic wave initially. Then you cannot use this electromagnetic software to calculate things like this, right? At least not in the initial stage, because that whatever the pulsar is emitting, it's not covered by this kind of analysis, right? Because that depends on what, then it will depend more crucially on what object is going in. So you assume that the initial states are inert, but still there is some radiation because as they are coming in, they are interacting gravitationally, right? Or possibly electromagnetically if they have charge, right? And that will cause radiation.
But if we don't know full information about that radiation, then how can we expect that the final
Full information about what radiation?
let's say these inert objects are coming close and
Yes.
getting scattered,
Yes.
as they are approaching, there's some radiation, right?
Yeah, so that we know, right? The C and G are precisely what gives the radiation from initial state, right?
Right.
Because they are accelerating in each other's gravitational field.
Right. But now let's say in addition to that, initial states also consist of some gravitational waves.
Yeah, so if those gravitational waves are falling into the scattering region, then it's okay, because then they get mixed and then they come out, right? But in the initial state, right, imagine that as if it's a binary black hole system, right, which keeps emitting gravitational waves as it's coming in, right? That information you will not know, right? So this is assuming that the initial particles are coming in, right, are gravitationally inert, right? They do gravitationally radiate, but that's because of the mutual interaction. Not that inside each of them there is a source of gravitational wave.
That has gone into this formula.
Yeah, that initial state, when I said P objects that are coming in, right? Those P objects individually, if there are no other object, right? It's assume that they are not going to emit any gravitational wave, right?
Basically, your binary pulsar has one momentum, not two. I mean, it is one.
Exactly, yeah.
That's the key point.
Exactly.
It contributes one momentum to your.
Yeah, and we assume that there is no internal motion that is happening, which is emitting gravitational wave. In that.
So I guess what I'm asking is that when you give this compensating formula,
yes,
where you remove the contribution from the massless particles
in the final state,
and add instead that combination there, which
Yes.
was in the previous. Yeah, this one.
Yeah.
So in this formula here, this capital P F is
Yes.
the final state massive particles.
yes, total momenta of the final state massive particles.
And that's PI is a total incoming moment
Yes,
initial.
that's
So
it.
that also includes the gravitational waves.
Yeah, that includes the gravitational waves. You are assuming that there are no gravitational waves that are coming in,
Okay.
but it can happen.
You're assuming in this process that there are no,
But you can have gravitational waves coming in, right?
but you need to know them.
You need to know them. Yeah.
Okay.
Yes.
Just to make sure I understand for the gravitational collapse of the black holes, roughly speaking, the incoming state would be when a bound state, when they've started loosely inspiraling towards each other. And
How many incoming state there will be when they are not bound? If you really strictly want to apply this formula, right?
It's a difference between
Yeah,
the bound state.
when they are not bound.
and state.
Right? Then each of them are gravitationally neutral, right? They are not emitting anything.
so even
And
earlier, let's
even
say
earlier,
even earlier.
yeah. So if you
before they
use over that time scale,
asymptotically-
yeah. So imagine that the two objects came from very far, right? Then they got bound somehow. In that process, they emitted some gravitational wave, and then eventually they disperse. Right? Then over that time scale, you can again apply this formula.
Hmm.
Right? But that means you have to wait for really long time.
Now you have to put the formation of the binary system into the box.
Exactly.
The interaction box.
Exactly. Exactly.
Okay,
Yeah.
but just suppose I'm only interested in using the formula for the final.
Even then, I mean, if you want to use that formula based on two things coming in,
Uh,
then you have to put that
Very
system.
long
Then you have to be very long. Right? If you are only interested in the final,
yeah.
then you just think of the initial state as one object, already bound. Right?
No, the reason I'm asking is, if I think of it as one object after the quasi-normal modes have run down, that's
Yes.
too late, no? Because then the final merger has already happened.
Yes, that is true, but nevertheless, right? If it has a supernova, right? Final explosion has already happened. Even then, there will be one over u piece, and now you over u square piece. So if it has a supernova instead of a binary black hole merger, right?
Okay,
Then there will be log u over u and u square and one over u piece.
okay. Okay, but what about a black hole merger? If I say the initial state is after the final ring down has happened,
No. Initial state is just one object, right? Which is a bound state.
but defined at what time in the spiral?
It doesn't matter at what time, right? It's some bound state of two objects, right? Which has a certain total momentum, right? That's how to count. But for that system, because it's a gravitationally active system, you cannot use the formula that I gave for the initial, the past radiation, right? Because in the past, it's radiating because of the internal motion of the system, right? But after the merger has happened, then you can use that formula at late time, right? Largely.
I see, but what, sorry to slow you down, but in the late time formula, you had the initial moment.
Yes,
And
that is the total momentum of the initial state.
And if I'm going to define the initial state as sort of some point in the inspiral, then what am I going to do in terms of those initial momenta there? So I have the two objects, they're
Yes.
not quite at asymptotic infinity, but
Yeah.
at some. So am I supposed to take their individual?
No, total
just the
moment.
total momenta
Yeah.
of the two systems?
Exactly.
Just change in mass will
Yeah,
account for that.
exactly.
I see.
That is the total momentum of that system. Right? And then in that formula, you have to put in all the gravitational waves that are emitted during that process.
Suppose the initial state was not a binary pulsar, but a binary, some atom bound by electromagnetism.
Yes.
Then also would have this, what would happen? It might still,
It will make,
I don't know, weird.
yeah, you start from something, then
Yeah.
during that process, it emits an electromagnetic radiation, suppose, right?
Yeah, and it inspire, I mean, maybe, it's a stable, maybe it's a, I don't know.
Yeah, eventually it is down state, right?
Hmm.
So depending on when you start counting, right? If you want to start counting from very far when it is an excited state,
Hmm.
then you use that as an input, incoming momentum,
Yeah.
and then the radiation that comes out because of the emission,
Hmm.
you put as part of the final state. Right.
But then you still don't have any of these Fs and I forget the names, P and F or whatever. Why you do that?
In that case, the final
The final state.
yeah, I think the final state contains only one massive object.
Hmm.
Then you don't have it, right? If you have a say radioactivity with alpha particle,
Hmm.
then you will have this. Okay, that's just an extreme example.
That's an explosion, then it becomes a.
Yeah, then it becomes like two particles coming out,
But
right?
Ashok, this is what I'm a bit confused about, sorry, but I mean, if you define your initial state as when they're loosely bound.
Yeah.
In spiraling, then starting from that time onward, there will be some gravitational emission and
Yes.
so on. Then you finally settle down to one black hole,
Exactly.
right? Then in your formula, the final state will include that radiation which comes out.
Yes.
So
But that will go away because that will go away if you use this formula, right?
but then you trade it for that. and
Exactly.
So then
Yeah.
it goes up.
It goes away, right? So the point is that two changes in that case. If you, depending on when you start, right?
Yeah,
The PI will change,
yeah,
right?
yeah.
And in that formula that I gave, or original formula, incoming state momentum, that will also change.
Yeah.
Right? And those will compensate.
I mean, the PI changing is that change, no?
Exactly, yeah.
Is that change?
Yeah. So because that formula will change, because if you use a different incoming state, right? Because the masses have changed, but this will also change. Yeah, and eventually
Compensated,
it will just compensate.
Sorry, but Ashok, I could have thought of this process also as two objects coming in.
If they are coming from infinity, yes,
Then you have to
right?
wait. very-
But then you have to wait very long to apply this formula.
Okay, but in some limit of that, this formula should agree with
Yeah.
this formula.
Yeah, this formula will agree, right? You just have to wait for sufficiently long time.
So sufficiently long time means.
Meaning the whole the time of formation, right? The final U is correlated with initial time, right? If you really want to start from a time when, say, it takes a billion years, say, right? For the two things to, suppose I spend billion years in that configuration, right? Then that billion years from now,
Is when you will be able to.
inherit will be able to use
No,
that
but
formula.
you said that this 1 over u and this u square log u terms,
Yes,
u to the minus 2 log, those are universal and they don't care about this additive shift in this time.
so they don't care about the additive to the time. The question is how long you have to wait
Yeah.
for this formula to be valid.
But this 1 over u term, the coefficient of that would be the same, right?
Would you know if you are starting with two different particles, right? Then the PI is the total P is the same,
Yeah,
but there will be different P's, right?
Yeah.
Instead of having one initial state, you'll have two initial states,
yeah,
right? So if you want to use that formula,
Yeah.
right, that will give a different coefficient of the 1 over u term.
yeah. So how is this consistent? That's what I'm asking. In what regime should I expect it to be the same? Why is it not?
Yeah, so that formula will take over at a value of u, which is larger than that 1 million years.
No, but we are looking at coefficients of 1 over u, etc. Right? So what do I do then to see that it matches?
They are in some point,
1 million
asymptotic
years
limit where u
later
is.
and subsequently.
Exactly, yeah,
That
this
is the-
formula will be valid.
You have to
Right?
wait that.
Yeah,
long.
it's what is called the backscattering effect. I mean, this is somewhat counterintuitive because how come what happened 1 billion years earlier, right, is affecting things 1 billion years later, right? But this is what the gravitational backscattering does. That what happened far in the past, right? Basically, that keeps scattering back and forth, right? And it affects the form of the waveform of that order of time later.
But in the level of the formula, then to see that it in the results after 1 billion, like when it matches, what is it that what is the limit?
There will be a correction term, right? Which will involve, see, this formula will go down. I mean, like E equal to 1 billion here, this formula will become very small, right? This 1 over u coefficient. But now that new formula will dominate. This one, right? Because here we are assuming that the incoming and final states are specified once and for all, right? If the incoming state had another past, right? And if you want to put that into picture,
Okay.
right? Then the formula changes, but it changes after that much time.
And can you just maybe give an intuitive understanding of this backscattering? Why is it that?
Yeah, I don't know of an intuitive understanding of this backscattering effect. It's basically the fact that the radiation, right? I mean, we are saying that it takes this log r term to reach the detector, right? R plus log r, right? That's the classical formula. But the actual way, what happens is it keeps going back and forth.
back and forth between one and one.
in that geometry, right? Because there's the whole phase, the configuration has some mass, right? Which produces curvature. Right? And the wave, when it propagates out, it goes back and forth between in that background. Right? And that is a backscattering effect.
But I mean, why is it so counterintuitive? Sorry, suppose, just to ask you, suppose a billion years earlier, you had this shell or whatever beginning to collapse. Now, some part of it will backscatter and so on. So the characteristic scale will remain 1 billion light years or so.
Yeah.
Now, when your final wave has to go out through that 1 billion light years, it will see all that in the course of it, or not. Is it?
Yeah, that is true. The question is, I mean, what happened in the past? Why should it affect things so much time later, right? 1 billion years later. Okay, I mean, maybe it's not counterintuitive, but
Sorry.
some of that seems to what is happening, right? That this backscattering effect, right? The time scale over which the backscattering effect remains is the time scale over which this collapse is taking place.
I'm going to talk about how any of these formula were derived.
Yeah. I was hoping to talk about this.
Okay, it would be nice if we can go.
Yeah. Okay, so here I have some numbers, right? That if you have this core collapse supernova, right? The strain is about of 10 to minus 22.
Strain is what?
Strain is what you will see in LIGO, right? This is the displacement divided by the overall distance, right? The fractional displacement, fractional change in the length. Right, so LIGO sensitivity is about 10 to the minus 21. Okay, but this really requires that it has to be a supernova in our galaxy and also with the parameters that are stretched to the limit. Right,
The emit part.
This is the mu part, also the b mu part, right? For mu, you don't have to say after what time. For b mu, it's after a second. This is the kind of thing you see, right? And second is the time that I've chosen because second is the time that takes the supernova to actually explode, right? So after a second, you can just think of the final states as just dispersed.
This is still amazing. It's just a single supernova, not some supermassive black hole.
That
It's
is-
at
yeah.
the edge already.
Yeah. In fact, for bullet cluster, the actual strain is much larger, right? It's that this change happens over 100 million years, right? So we cannot detect it in LIGO. Right, but if it may have some consequences in cosmology because different parts of the universe will of course have different states, right? So I don't know whether one can use it in some way.
So this supernova etc. possibly could be this B mu and B mu effect can be detected.
Yeah. So the supernova B mu is there, is non-zero.
And in the merger it is 0, so we cannot.
Exactly. Yeah. So merger, the point is this is you can say that this is a null prediction, right? That you shouldn't get a non-zero B mu. Yeah. And the other thing we are trying to correct the explode so that see this kind of collision is happening everywhere in the universe, right? So that this can have some stochastic effect that each individual collision, one star passing another, right? Maybe a small effect, but overall, right, there will be some stochastic effect which may be observable. So that's I don't know whether that's true or not.
Sorry, Ashok, why is it that in the supernova there is a B mu and in the merger there is not?
Because in supernova, the final state there are more than one massive particle.
More than one mass particle.
Where it basically spits out a lot of matter.
But there is some assumption about what is the distribution of the momenta for those massive particles.
Yeah, so the assumption basically comes from some observation that the neutron stars, which are the remnants of supernova,
Okay.
is type 2, they actually move with very high velocity, right? And the idea is that high velocity comes because during that the explosion, right, there's an asymmetric expulsion of matter, so it gets a kick, right? Using that, you can estimate how much matter could have been expelled in one place.
But most of the stuff coming out is not massless. In the supernova.
Not really, no. There are massive particles which are coming out, right? Because there are jets which are coming out which are massive. Now, some outline of the derivation. Let me see how far I can go. Okay, the soft graviton theorem, this derivation right, requires several assumptions involving infinite divergences, but I'll just outline the argument, right, without giving the too much details. So the idea is that in quantum field theory, the scattering amplitude A gives the probability amplitude and the mod A square gives the transition probability. So let's suppose that we know the scattering amplitude A for transition from some incoming state P to some outgoing state Q. Okay, so P could contain a set of particles, Q could contain another set of particles. Okay, and let's suppose that we know the scattering amplitude for P going to Q. Then what soft graviton theorem does is to give the transition amplitude for P going to Q plus some low energy gravitons. Okay, any number of low energy gravitons of a certain energy, it can calculate the scattering amplitude for that process. And this is the purpose of soft graviton theorem. And it does it in terms of the original transition. So we take such formula and calculate the classical limit. And the way we take the classical limit is to take the states P and Q to consist of very massive objects. And then we compute the transition probability for P going to Q plus m low energy gravitons, each of certain energy and certain moment. So once you apply the soft graviton theorem, what happens is that this transition probability takes a form like this, where R is a constant. So if you said m equal to 0, then that's the transition probability R. So R basically is a transition probability from P to Q without any soft gravity. That is a very complicated object. We don't know what it is, okay, because that's P equal to Q. S is what is called the soft factor. This factor is universal. It depends only on the properties of the incoming and outgoing objects, because this is what tells us the amplitude for P going to Q plus low energy gravitons in terms of the amplitude for P going to Q.
This
So
comes from these propagators that we had extra.
exactly. So this S comes basically the leading soft graviton theorem that comes from the extra propagator that will come for every gravitational attachment.
So the gravitational waves are to be treated separately because you take PQ to be very massive objects.
So as long as they carry, you don't have to take very massive, as long as they carry a lot of energy, that's good enough. Right? We really use the fact that they have a lot of energy. I mean, we will see where that information goes in, right? So far, it has not really gone in very much, right? It will come, yeah.
In terms of diagrammatics, this is just literally each soft graviton coming out independently, right? And
Yes.
just the both-
And you have to sum over, yeah, exactly. Each soft graviton coming out independently and you are using the Bose statistics, right? But the fact that for m soft gravitons, the factor is S to the m, that is the consequence of soft graviton. Right? In general, if there are, if the gravitons, if you think of a scattering amplitude, right? The gravitons are latticing everywhere in the diagram. Then there is no reason why the m gravitons will get a factor of S to the m.
But if it's so soft that its emission doesn't affect the trajectory, then
That's when this happens. Exactly.
Got it.
Okay, so this soft factor one can calculate. This is the soft theorem, in fact, right? And it depends only on the properties of the incoming and outgoing objects. And the important point is that this turns out to be large in the classical limit. Okay, that's when you take the external states to have large energy, then this S becomes large. So given that S is large, now we can ask, where does this, see, quantum mechanics allows arbitrary any number of gravitons to be emitted, right? It just gives a probability for emitting certain m number of gravitons. But we can now ask, where does it have a P as a function of m, right? This quantity, and one finds that for large S, it actually has a short maximum at m equal to S. And this means that even though quantum mechanics allows emission of arbitrary number of gravitons, the transition probability is peaked around a particular number, right, which is S. And this is what you identify as the classical number of low energy gravitons. And then if you want to know classical flux, you just have to multiply by h bar times omega, right? Because each graviton is carrying h bar omega energy. And the nice thing about this is that S has factor of 1 over h bar, but once you multiply by h bar omega, the h bar goes away. Right? So you really see that this is classical, right? So the h bar goes to 0 limit exists, and that's a classical formula in terms of the incoming and outgoing moment.
So this suggests that we just model it as follows. You have the outgoing state, which is a source, and you solve Einstein's equations in that source. Don't change the source.
Something like that, yeah. We'll see, okay, it's not, it's almost there, but not, there are some features that one has to keep track of.
Sorry, there was a question.
So yeah, so all these M gravitons are like carrying same.
Yeah, we can, I mean, here I have simplified by saying that, let's say M gravitons each carrying this much energy, but you can assume M1 gravitons carrying energy h bar omega 1 in some direction, M2 gravitons carrying h bar omega 2 in some direction. It will just have a corresponding formula, right? S to the M1. Exactly, it will be like a coherent state, right? M1 graviton in one bin, M2 graviton in another bin, and so on.
And is this all at the level of leading soft theorem that?
No, this is leading and subleading.
And subleading.
Yeah, leading and subleading.
All immediate subleading or not subleading? I mean.
Sorry, this is leading, subleading, and sub-subleading.
Oh.
I mean, it works for up to
And then
up to
what
sub-subleading. One has a soft graviton theorem. After that, you don't have.
So this will get corrections from those processes which somehow don't
Yeah, after that, the point is you lose this structure.
Yeah. Well, or you could say it gets corrected or you really lose it. Can't.
As far as you know, you will lose it, but maybe there is some sense in which maybe in the classical limit to recover it, right? Here the point you have this structure even before taking classical limit.
You might suggest that if you just include the kick a little bit, I mean, you solve the classical problem, but you include the kick, then you might have a structure like that.
Yeah, I'll discuss the classical derivation, right? Maybe that will become very clear how we have it, how we prove it classically.
Here when you say subleading, it's subleading in the total energy of graviton being
Subleading in the omega, subleading in omega.
one graviton.
Yeah, one graviton energy, omega frequency omega.
These are the ones that would give rise to successive coefficients in this UX1 only.
Exactly. Yeah.
Okay.
Right. The expansion of S will basically give you the successive coefficients.
And this, when you say S is large, it's 1 over h bar order.
Yeah, exactly. Yeah, because you are taking the external states to have energies, right, that are large, right? So it's basically 1 over h bar, which makes it large. Yeah, so then the idea is that once you have the classical flux, you can translate this into a classical waveform, right? Because the flux has an expression in terms of the waveform, so you can construct the waveform back from there, from the flux.
And this energy is S h bar omega is of same order as DNQ or H.
S h bar omega, yeah, here once you have individual omegas you take to be small, but the total you don't have to assume anything, right? So this can be of the same order as PNP.
But then it will not react on scattered particles.
That is true, yeah, because you are applying this formula one at a time, right? For each graviton we have the formula, right? And then we derive it. The total emission could react back on the original formula. Okay, but as I said, this kind of approach has various issues. Okay. One is that the usual sort factor is infinite divergence. Okay, so you have to somehow regulate the infinite divergence by using some physical principles. The second problem that it faces is that there's this reconstruction here. I said that once you have the energy flux, you can construct the waveform, right? But what you can do is really that you can construct the magnitude of the waveform, right? You are looking at a Fourier space. So the waveform can have a complex phase, right? The frequency dependent phase that you cannot reconstruct from this analysis, right? Because it only depends on the mod square. Right? So you have to do a separate analysis to determine the waveform, right? Which is outside the soft theorem, but there are ways to do that.
So the same kind of roughly the same kind of soft analysis of scattering allows you to obtain even the complex, the phase.
Yeah, it's basically what happens is that this Coulomb phase, right? You have this equal to I omega r plus I omega log r, right? Now the log r is ill-defined, right? R is a dimension full quantity, right? So what happens is that to log r you replace with log omega r, and that's what produces the phase, omega dependent.
You're allowed to use the results from soft graviton theorem is the reason is that I don't have very late.
That you don't have?
You don't have very late names, that's why.
Yeah, exactly. Right? Because small omega translates to that time, right? Which we'll see how that happens, right? I'll just when I discuss the classical derivation, I think because classical derivation is much neater, right? I mean it's clear, you don't have to make any assumption, right? It's just more complicated. Right? That's why to derive these results is first useful to use soft theorem, but then to give a complete derivation, you can go to classical physics. Okay, so here is the direct classical derivation. So the goal is that we want to compute H mu or equivalently E mu that is generated during a collision process. And to do that, we write down Einstein's equation. And for us, this is Einstein's equation, which of course looks very deceptive. Right? This box here is a standard flat space Laplacian. So what we have done here is that we have basically taken the Einstein's equation and taken everything that is not this to the right hand side. Okay? So this is the linear part, all the non-linear part has gone to the definition of T mu. Okay, so this of course you can always do, right? You just define T mu appropriately. So this looks simple, but it's not really simple, right? Because of this fact that the right hand side depends on E mu in the non-trivial. Okay, let's proceed. This is probably the key point in the analysis. So what we are going to do is to define the time Fourier transform. E tilde mu nu, we just take the Fourier transform in time, which is here, and this is just a phase, right? Which is basically telling us that we are taking the Fourier transform not in with time but in the retarded time. T minus mod x is roughly the retarded time, right? But this is just, you can think of this overall phase that we use here. Now the point is that we are looking for these behaviors. E mu nu goes to a constant for large u, or E mu nu goes to 1 over u for large u, or E mu nu goes to log u over u square for large u. You can translate each of these into the dependence on omega. Right? If this goes to a constant as large u, then E tilde mu nu goes as omega inverse. If this goes to 1 over u for large u, then E tilde mu nu goes as log omega. And if this goes as log u over u square, then E tilde mu nu goes as omega log omega square. Now notice that here I have not distinguished between whether it goes like this for large positive u or large negative u, right? That turns out to be correlated with the I epsilon precision, right? So I should have written here omega plus minus I epsilon inverse, where plus I epsilon versus minus I epsilon is will depend on whether it goes to a constant at past or future. Similarly for here. Okay? So 1 over u in the past will correct the coefficient of some omega log omega plus I epsilon, and in the future will correspond to will be related to the coefficient of log omega minus I epsilon. Okay, so to distinguish between past and future, you have to keep track of the I epsilon formulas. So what we need to do if you want to do the analysis for E tilde mu nu is to look at the terms in E tilde mu nu which are of this type. And one feature that is common between all these terms is that they are non-analytic at omega equal to 0. Okay. Non-analytic doesn't mean divergent necessarily. Right? These two are of course divergent at omega equal to 0. This one is not. But non-analytic means that if you take derivative with respect to omega for sufficiently large number of derivatives with respect to omega, then it will diverge at omega equal to 0. Right? And that we're going to make use of this in the subsequent analysis. Okay, let's leave this aside for a while and turn back to the equation. Okay, box C mu nu equal to minus 8 pi g T mu nu. This can be formally solved using the zeta dependence function. Okay, but of course it's not really a solution because T mu nu depends on E, right? In a non-trivial way. Nevertheless, if you start with this and you substitute here, okay, this expression, the time Fourier transform, then it's a relatively simple exercise to show that if you take the time Fourier transform of the retarded Green's function, right, it has a simple structure. It becomes 1 over r or 1 over mod x times e to the minus I k dot y, where k is now a 4 momentum, but is determined in terms of omega. So this is basically telling us that if you have a equation like this, then the time Fourier transform of E at large distance, large x, is related to the full Fourier transform of T mu. Okay, that's just a mathematical statement. I mean, you can easily prove it by doing this T integral using an appropriate starting point for large x.
So this assumes that y is localized in some region.
Yeah, this assumes that y is localized in some region. Exactly.
Reduction to why is it?
That this integral
Okay.
is localized in some region.
Region of Y.
Yeah,
Where
yeah.
do you assume that?
Okay, it basically assumes that when you are calculating this x, right? This is small, that this is localized away from where you are calculating. That's all, right? That it need not be localized, but the distance from the point where you are calculating this from the source is small. Right? That's all. Sorry, distance is large. Distance from the source is large.
I thought when you say large X, you mean in that integral, the support for T mu is spread over some region, say L, and you're looking at mod X much bigger than L.
Yeah, that is true.
Okay.
But this of course cannot be strictly true because those particles are also flying away, right? Towards infinity, right? So what you need is that the point X where you are calculating is far away from the sources, right?
From all
That you don't have a particle that is passing through you, right? Then of course your gravitational effect will be very defined. Right? Imagine one of the objects is actually passing through you, right? Then you cannot use you have a defined gravitational effect. Because we assume that the actual amount of force that is passing through you is tiny. Okay. So here is the formula again. So now this integral of course runs over everything. We divide this integral into two parts. One is part called the scattering region, where this is a region of large size around the point where the scattering is taking place, and the other one is asymptotic region. All you will assume here, this scattering region has a finite size. Okay, that size you can take to be the basically roughly the size over which the actual interaction takes place. Now you see that we are looking for non-analytic terms in ET now, right? Which means that we are looking for terms that will diverge once you take sufficiently large number of derivatives with respect to omega. If you look at this expression for E tilde, and if you take derivatives with respect to omega, we see that it is going to bring down factors of y, okay, with t mu nu y. But this integral, however many factors of y you bring, will never get a divergent contribution from a finite integration.
From finite
Integration, right? Because this is a finite integral, you are integrating over finite region, right? So it's not going to get a contribution, divergent contribution from the finite integration region. So which tells us that contribution from any finite box you can ignore. If you are interested in calculating the small omega behavior, right, you can ignore the contribution from a finite region. Okay, and you can focus on the contribution from the region outside this range. Okay. And this, of course, is what makes life simple. Because outside this range, gravity is weak. Okay, because you have gone far away from the region where scattering is taking place. So this is what I've said here. So here, what happens is, first of all, only in this region, all the forces between particles, right? The non-trivial forces have died down, only the long-range forces are still persisting, right? So when you want to calculate the particle trajectories, which will be needed for computing the waveform, you can use weak gravitational coupling, right? The long-range force between the particles. And E mu nu is small, so you can so the expression for T mu nu, which also had contribution from gravitational fields, right? You can expand in parts easily in E mu nu, right? Because the gravitational wave for strong E, right, it's a complicated non-polynomial function of E, right? But because you know that we are calculating the contribution from this region where field is weak, right? You can expand it out.
So this expansion is same as the 1 over u expansion.
This will turn out to be the same as 1 over u. So we now basically solve this equation iteratively.
But then some region, suppose you had a singularity in the T mu nu.
If you have singularity in the T mu nu, then of course there will be a problem. But we don't expect real singularity in T mu nu, right?
You moved all the other sides, the Einstein equation, other than, I mean,
That is true.
is all not.
But as long as the fields are non-singular in that region.
Black holes are not allowed.
Black holes, we are only integrating outside the horizon, right? So anything inside the horizon cannot send any signal anyway, right? So those sources you can just ignore. Anything inside the black hole horizon, right? And outside the black hole horizon, there is no singularity. So if there is a naked singularity somewhere there, right, then that could affect the charge. So you are assuming that there is no naked.
Yeah, you're written outside the black hole.
Yeah, because I mean, if you look at, we are looking for a signal from this region, right? So if there is a black hole here, inside the horizon, whatever happens, that signal is not never going to reach the observer far away, right? So this integration can be restricted to outside the black hole. Because retarded Green's function will just vanish, right? You have multiplied by retarded Green's function. Right? So that will just vanish if say y was inside the black hole. Right. Sorry. Yeah. So here I have shown the various equations that go into this iteration. Right? As I said, we solve this iteratively. Right? So not all the equations have been solved. So here are the equations for the energy momentum tensor. T mu nu is sum of the contribution of the energy momentum tensor of the particles and the energy momentum tensor of the gravitational field. TH has a very complicated expression, which is I have not written it down. But most of the effort in calculating this iterative process goes into dealing with the TH, right? Because TH is quadratic in H. So basically, so what happens is at the end, you do loop calculations in quantum field theory. It's equivalent to doing loop calculation in quantum field theory when you solve this iteratively, right? Because you solve it in momentum space. Okay? So you get loop integrals. The only difference is that the propagators are not quite the Feynman propagators, they are retarded propagators, right? And instead of, so that's the kind of difference you find, right? Otherwise, it's basically doing loop calculations. It looks like loop. It's not. There's no H bar. Yeah, there's no H bar. What I'm saying about the actual iterative solution when you do, right? In momentum space, right? You get analogs of the loop integrals. Right, that's all. I mean, it's just classical scattering, but you have to. Yeah. I mean, normally you would think that only T-level diagrams are here, right? But that's not true. Yeah, if you actually go through this, right, you actually get that analog of the loop integrals.
For electromagnetism, there's nothing. There's no T, right? TH, sorry.
For electromagnetism, that's why it's much simpler.
So simple.
Exactly. Right?
And then there is no expansion also for E.
No, there is expansion because TX has to be solved iteratively, right? Because if you see this, what you do is that you have to solve for E, right? And then you have to plug that in both here as well as in the trajectory equation.
Oh,
right? The trajectories will get corrected. So
Okay.
for electromagnetism, trajectories will still get corrected.
Okay.
Right? So there also there's a whole expansion,
I see.
right? Which you can calculate, but based only on the correction to the trajectories.
You're taking into account the correction in the trajectory because of emission, is it? The sort
No, because these particles are still having long-range gravitational force, right? So these particles producing E mu nu, right? That E mu nu, under that E mu nu, this is accelerating.
So I was wrong. When you wrote that formula for the soft factors, it seemed every subsequent insertion didn't care about the previous. I mean, it was just S to the M over M factorial.
Yeah, but the omega, the U expansion does care.
In a sense, that formula, the S to the M, is clever enough to compute.
Yeah, always.
It's kind
Yeah.
of amazing. I don't fully.
Yeah, I mean the subleading one. So the point is the leading, the memory, right, comes from the analog of the tree diagram. If you translate to the actual calculation that goes into solving this iteratively, the leading contribution is the memory. Right? Then the first iteration generates the 1 over u piece. Okay, or equivalent to log omega piece. Okay? The second iteration generates the omega log omega square piece. Okay? And you can see that this log omega log omega square, these are all basically coming from infrared divergent effects. Right? Here there is no genuine infrared divergence, but there is apparent infrared divergence in these integrals, right, which are all regulated by the R. Okay, that's the cutoff.
So the reason you don't see like 1 by u and like log u by u squared in terms for one massive particle was that it was not interacting with any.
Exactly. Yeah. So one massive particle is not accelerating under anything, right? Because it's just moving, it's a free particle. Exactly, that's exactly the point.
150, so.
Not too late.
So when these trajectories are getting affected by like reactions, the final momentum will also get affected by that,
Exactly.
right? And then you express the whole thing in terms of the final momentum.
Exactly. So that's what I've said. The boundary condition, the way we put it, right? That for the final state, we put the final state condition. That dx zeta in the final as tau goes to infinity is given by this, right? And then we integrate it backwards. Right? For the incoming ones, we integrate it forwards. Right? So that's the main.
That's another complication.
Yeah, well, it's not a complication. It's not what we normally would do in a classical mechanics, right? But what soft theorem is teaching us is the kind that the questions which are simple answers are the ones who have to specify the initial momentum and the final momentum, and then calculate the gravitational radiation for that process.
See, this comes out in a sense from trying to reproduce the soft graviton quantum answer, is it? That you,
Yeah,
I mean, it's
this
the
comes.
thing to do
because-
because you specify.
Yeah, because this comes because we are trying to solve. We are trying to find out what is the radiation for a given set of incoming momentum and given set of outgoing
So
momentum.
you
Right?
have to specify.
That's our
the
data.
final. Yeah,
Exactly.
Okay.
Right. So that's why you specify the final set momentum, and when so you solve it, right? That you integrate the trajectories from future to past in the final state, and from past to future in the initial state. And in of course, you use the standard retardant, right? It's constant. Okay, and you just keep iterating this, right? And as I said, up to first, so leading order, which is analog of the tree diagram, gives you the memory. Then the next order, which is one loop, gives the 1 over u piece, and then the 2 loop gives you the 1 over u squared of u piece. And in principle, this can be continued, right? There is a soft theorem for this, but this procedure in principle can be continued to higher order.
It's basically solving the instance equation in the presence of sources which are moving.
Exactly. Yeah. Right, which are coming in from fast and which are going in very far.
What whatever happened at the center, during the starting.
Yes.
All of that will that produce a faster than power law because
Yeah. I think that they need not. I think whatever happened during the scattering will probably produce faster than power law decay. Right. There are other corrections to power law decay which could come from the multiple moments of these objects. Right. The initial incoming and final particles may have also higher multiple moments. Spin, for example, right? The spin hasn't entered this formula. Right. We have not assumed that these particles are not spinning. Right. What one can show that if the particles are spinning, then they'll affect the 1 over u square piece. Right. Not 1 over u square log u piece, but 1 over u square piece. So similarly, all the higher multiple moments will affect those. But I think whatever happened during the scattering process will have faster than power law for large.
What in the classical calculation is the analog of the fact that you're computing the leading logs? I mean, that comes out, is automatic just if you do the classical analysis, or that is to say, at 1 over u square,
Yes.
you may have log u square and then also a log u piece. I don't know.
Yes.
But the log u piece is not so universal.
Exactly. Yeah.
And if you do the classical calculation like this, is it that you just compute the analog of the log u square piece and not the log u?
Yeah, because what to find the log u square piece, right, is universal. Right? Log u piece will require more information.
Okay, the classical thing will show that to you.
Exactly. Yeah.
The answer will just depend on p's and p primes.
Yeah.
Is always
The energy momentum tensor, for example, right? Here the Tx, if they have multiple moments, then the Tx will have additional terms. Right? So those you have to take into account.
Okay.
Right?
Okay.
Similarly, yeah. So here, for example, the trajectories, I mean, you are only here I have only said dx zeta, right? But for example, the constant piece of x could also affect, right? It doesn't affect to the order that we are showing, but which is the impact parameter, right? Not just the final momentum, but how displaced the trajectory is that relate to each other, right? That information will also go in at some point, right? So all those will be subleading in this expansion, right? The leading terms seem to only depend on the moment.
So we will see that the log u by u piece is not there. You said it's part of the result. Well,
That log u, because the leading contribution to divergence that we get is log omega. Right? Then there'll be omega log omega square and so on. Log omega translates to 1 over u.
okay.
So if you want log u over u, then there has to be log omega square piece. Right? That one can check that it's not there in this analysis.
1:15,
Yeah, no, I'm
No,
done.
you don't hurry, I'm telling the audience.
Yeah.
Sorry.
So, what happens at 1:15?
Sorry, you have faculty lunch,
Oh,
then
I see.
we run the risk of.
Yeah.
This the stress tensor, you said when there is spin, there is extra terms in stress tensor.
Yes, that's right.
And that thing, that correction has been computed or?
Yeah, Vishwajit and Devendra, they calculated this 1 over u square. Right, from soft theorem, there is a prediction and they check that prediction also what's that in the classical calculation. So that correction comes out at 1 over u square order, right, as opposed to 1 over u square order. Okay, so I'll just end with some comments and some future directions. This, in fact, I have already emphasized that the classical analysis certainly is straightforward. We just solve these equations iteratively, and doesn't involve the complications of interdivergence and the phase ambiguity. But the quantum theory, that derivation from soft theorem, is significant because this is what really teaches us the right question to ask.
You said this, but what do you mean, Ashoke? I didn't understand. That it teaches the right question.
Yeah, I've said
Oh.
that if you are doing usual classical setup, right?
Uh-huh.
Then what kind of question will you ask? You will give the initial state and then you will say calculate the final state, right? Evolve, right? So you have to calculate the final state, what the momenta of the particles will be in the final state and the radiation that comes out, right? That will be a much more complicated one, right? It's a quantum theory, right? It's in EFTs when you have the S matrix kind of question, right? You specify initial and final state and then you ask something interesting about it,
I
right?
see.
So here, what soft theorem is teaching us that if you specify the initial and final momentum, right, and then ask for what radiation comes out of this, right, that has a much simpler answer, right? So that's the lesson from quantum field theory. So that kind of question you would normally not ask in classical physics, right?
Now I understand. I see.
So that's basically what I wanted to
Interesting.
emphasize here. Okay, and here is some possible generalization, as I said, that there is reason to believe that these coefficients are also universal, okay, that they depend only on the momentum of the particles. And the question is, can you compute them? As I said, for electromagnetism, it has been computed, right? In fact, we did this calculation with this graduate student here. And there is a universal answer.
I see.
The problem in gravity, of course, the soft theorem is not useful anymore, right? Because soft theorem only wants subleading order. And beyond that, there's no soft theorem. But the classical analysis can still be possible, right? And the ultimate goal is to see if we can use these results in reverse, right? Namely, that by measuring the gravitational waveform in the detector, we can measure these coefficients, right? And if we can relate these to incoming and outgoing momenta, then the question will be whether by knowing these coefficients, you can reconstruct the incoming and outgoing, right? Because that will be like reconstructing the event from the. That's it.
So we only had a few questions during the talk.
Zoom audience, is there anyone?
I think the audience must have decoupled.
So, just to say, just to understand this last slide, you expect, I get the feeling that for gravity also, you've already done it for QED, but in gravity also, these leading log terms will be expressible in terms of
Momenta, yeah. If we just do naive power counting, that seems to be the case, but you have to really, do some hard work to figure out. Unless you actually get the coefficient, it's not a momenta, right? It's no one wouldn't want to make a claim.
Suppose this gravity was corrected, does it change any of these things or? Like,
I think if gravity was corrected by higher derivative terms, for example, it will not affect this part, but the subleading ones I think will be affected.
I mean, 1 over u.
Yeah, I think 1 over u kind of, or not 1 over u, the 1 over u square, this kind of thing, right? Those I think will be affected.
So but 1 over u square is anyway. It's not.
No, 1 over u square log u is what you calculated.
Ah,
1 over u square coefficient, we said that there is a formula in terms of the angular momentum that the particles carry. Right, but if there are higher derivative corrections, I think those coefficients will start getting affected.
That also has been computed then.
No, those have not been computed. In principle, if somebody is used to doing loop calculations in quantum field theory, I think they can do it. Right, it's because you get exactly 4 momentum integrals. Right, the propagators are different. Right, so
But I'm sure that any such correction will be suppressed by frequency over the scale for the higher corrections, right?
yeah, that's
So, I mean.
yeah. So those coefficients will come. Yeah,
Very small,
exactly,
right,
yeah.
compared to.
Yeah.
From the action, I mean, that's. where-
Yeah, from that.
Action, I mean, like.
Yeah.
So.
Exactly.
it will be
Yeah.
small.
and these loop integrals that you're talking about that appear at the technical level, they would, this 4 momentum integral, would there not be any divergence inside? One can just see that they're.
No, they are not divergent. Okay, there are divergences which you can identify, for example, the self-energy corrections, right? If you have a particle in gravity, right? If you just directly calculate its gravitational energy, you have the same kind of problem that the electron has, right? The Coulomb energy divergence, you just absorb into the mass of the particles. Yeah, exactly. Right? It's like a classical generalization, let's say.
So. For Young-Mills, you would imagine this calculation would be easier or harder?
Young-Mills, I think it will be harder because of this non-linear interaction. I think it will be much harder.
No, I mean compared to gravity.
Even compared to gravity, because Young-Mills has what's infrared behavior compared to gravity.
I was going to ask if that is easier, then maybe this doubling.
Doubling, yeah, but I think Young-Mills will be harder. That's my feeling.
Are there any known soft theorems for the Young-Mills?
Yeah, people have worked, on soft theorems for Young-Mills also. Right, yeah, but Young-Mills, for example, even the leading soft theorem gets corrected, I think, by infrared, by quantum corrections. Right, which is unlike in the case of gravity and electromagnetism, where the leading soft theorem is not corrected. Sub-leading ones start getting corrected by quantum mechanics.
So one question, can one do this analysis for the higher spin theory, massless higher spin theory?
In principle, yes, except that we don't really have a massless interacting higher spin theory, right? So it's there's no starting point. And if you try to do it in ADS, then in ADS, so there is a soft theorem, right? Because you can't really go to zero momentum.
If there are no further questions, let's thank Ashok for it.
Yes.